morning, everyone. Welcome to day 12 of writing a TCP/IP chat application. This might be the last day. This is almost certainly either the last episode or the penultimate episode, which is a term I forgot to use last time because it sounds really smart, but it actually just means second to last. And I was surprisingly old when I learned what that word actually meant. But it's a cool word, penultimate. Anyway, all right. See some people in the chat. If this is the last day, now's the time to ask your questions. So I said last time that I think I was done with the code, and then I realized after ending that stream, actually I still have a couple more to-dos in the code, so I definitely want to clean those ones up at least. So I'm just going to start off with a really quick code cleanup, and then I'm going to do kind of an overview of, and I know I've been doing overviews as I go along, but one final overview of here's what we've done, here's the important lessons in TCP/IP protocol design, and here's how we handle them in this code. Maybe a bit of an architecture overview too, and I'm going to be actually writing the README. I realized also after last stream that my README is empty, so I want to get some good information in there. Some pointers to good resources and things like that. And then I'm planning to spend a bit of time over what is not done, things that you might want to think about doing if this is a real protocol, but I'm not going to do myself, unless you all really convince me to do it. So I'm going to be covering some things that are not done, that you might want in a real world production application, and then I want to take some time left, if I have time left. I only have an hour this morning. But I'd like to take some time left and go over a bunch of tools that are really, really useful when you're writing a TCP/IP application. Most of the time you're only writing one side of it, and your implementation is initially not correct. I don't think anybody writes a correct implementation of any TCP/IP protocol the first time. And it's been easy for me because, for one thing, I've done this several times in the past. I've written a few different TCP/IP applications, and so I know where the most common pitfalls are. Secondly, I control both sides. And then thirdly, I have some great people in the chat who are pointing out bugs as I'm writing them. Okay, so that's great. So I have some advantages that a lot of developers don't have when they're writing TCP/IP applications. I'm going to go through some tools that I've used in the past, some of which I haven't used yet in the development of this app, but are incredibly useful when something's going wrong and you don't know what. So, 2 to-dos are in my project. Thank you, Michael. Yes, I'll clean both those up, and I think they're both discards. So let's go ahead and do that right now. Let me switch over to my computer here, and let's just search for to-do. My computer's a little bit slow this morning, and we're not sure why. But okay, so we've got this discard. Actually, this one doesn't even have to be a discard, because in this case we're on the client side, we're in a GUI application, and this button click here, I can actually await this. I'm going to go ahead and do that. That should work. So I'm just going to go ahead and wait. Oh, that should be async. And we'll do that. I apologize for all my ums. It is something I'm aware of. My 6-year-old daughter was watching one of my streams over the weekend, and she started imitating my voice. Blah, 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 oh yeah, I say a lot, don't I? Something I'm working on. All right, so we've got this process socket async, which shouldn't ever return until the socket completes. And we do have this top level try catch, so this could be async void, because it's got that kind of structure. It's infinite. It's not really infinite, it's just as long as the socket is connected. And then it's got that top level try catch. So this is really a main loop, right? This is a main loop in our client application. But because this is a GUI app, I can just say, I'm going to await this, even even if it doesn't complete, because it's not going to interfere with anything on the UI thread. This, since we're awaiting, other things can happen on the UI thread just as easily. Yeah, so I think I'm just going to leave that as that. And then my other one is on the server side, right? Yeah, I fixed all the ones like in our chat protocol library, which I call Chat API. So let's see here. Monday, says Michael. Yes, it is Monday. Monday may not be the best day to try to finish this up. Let's see. All right, so we've got our server app here, and in this case, we do actually need like a top level async void or a discard. I'm gonna replace this with an async void, because this is again a one of those main loops where you've got the loop handling all the messages. It's a top level try catch that also handles this connections list. Yeah, I'm good with that. I'm just going to make this an async void. And again, this is, and I'm going to rename it to be like a main loop here, just so that it's clear. Again, this is not something you normally do in async and await, but it's something that I'm going to do for this example. If this was real world code, I might, it depends. Like if this was like the whole purpose of this app, this is the whole purpose of this app, right? I have one server app that is a chat server. If this was a part of another app, for example, if I'm spinning up a chat server as part of something else, and I don't want to take down the entire app, which is what an async void will do if you have a top level exception in here, outside of this try catch, or say in this, if you've got logging in here or something, and this throws, then the async void will actually take down your entire app at that point, which is fine for here because my chat server is the application. If the chat server was like embedded in an application, then I'd probably want all these main loops to be async task, and then have some kind of like, something awaiting all of those main loop tasks that then I can log a top level fatal error or whatever and restart the entire chat server without actually restarting the application. But in this case, since the chat server is the application, async void is fine and it's simpler. So that's my reasoning behind that. Although normally you should avoid async void. Boy, my computer is really slow today. All right, but it did actually compile. So Freddie says, inside the while the accept await. Okay, right. Yeah, so when we're, this awaits, and then this, I'm just kicking off as like, not awaiting it. It's in an async void, so it can actually crash the app. All right, so yeah, I'm gonna do this here, and I think that's the last time I'm gonna touch the code here. We will see. So we've got our chat and server complete now, and so what I want to talk about a little bit, and I'm going to put some of this in the README. And let's start with copying. I've got this brought up over here. Yes. All right. So I've got a pointer to my playlist here so that people can find the videos from this. And let's see, what else do I need? I'm also going to want to talk about like what the main points that we've done. So this is going to be, I know I came up with a term for this. It's a minimal correct implementation. Because you can't really take the user interface that we have and say this is a minimum viable product, right? But it's kind of the same idea, just the implementation parts of it. So what we have is message framing to translate the streams of bytes to streams of messages. We've got error handling. And the key points around error handling is to always be reading. And this lets you detect errors quickly. As quickly as possible, actually. The other part of error handling, both of these kind of fold into error handling. I don't know if this really belongs into this header or not, but I'm going to say asynchronous APIs. So we don't need, because that kind of falls under the always be reading. If you're always reading and you're also writing, you don't want 2 threads per socket. So we don't need multiple threads per socket. And the other part that goes along with this is closing. So close both streams. You know, I just, because some of the knowledge may not be here. So what I want to say is each socket connection is 2 unidirectional streams of bytes. So that's the assumption behind what I'm saying here. So when I say both streams, I'm talking about both of those unidirectional streams on the same socket connection. Create both streams for a connection at the same time. And this is so that both sides can detect errors as long as data is still being transferred. Okay. Oh, and keep alives. That's the other big thing. Keep alives to detect half-open. To detect the half-open scenario. I'm just going to leave that. Half-open is a decently enough Googleable thing, I think. So I don't want to write out all the reasoning behind everything in the README. So let's see here. Should pop open my chat here. Okay, just making sure if anybody says anything, I got it. So I've got a description of our minimal correct implementation. And you know, I'm just going to stick my little. There is no such thing as a simple TCP IP application, but this is pretty close. All right. So I've described the minimal correct implementation. This is what this implements. I was going to say that this repository is a minimal correct implementation. And it's actually not quite minimal because we added the request response, but that's so common, I wanted to include that as an example anyway. So, so let's say overview of the chat API. Not the cat API, although that does sound like an interesting project. I'm going to say the chat API. Architecture. So in our chat API, and I've gone over this several times, but we've got, I've gone over it several times in the video. We've got this pipeline socket, first off. Which is kind of like the network stream, but using system.io.pipelines instead of stream. And then our next level is the chat connection. Now the chat connection actually does several things, and I've gone back and forth on this on the videos. I don't know if you've noticed me vacillating of, hey, I should probably split this out. No, I'm going to keep it in the same type. For this simple kind of application, I'm keeping it in the same type. If it was a more complex app, I would seriously consider splitting out some of these responsibilities, because the first thing it does, well, actually, I'm going to back up here and say, so the pipeline socket provides two unidirectional pipelines of bytes. Right. And then the chat connection provides two unidirectional, I want to say stream here, but I don't want to mess up, I don't want to confuse people. It's not like a stream, like the stream class, right? So two unidirectional channels, I'll just use channel, since that's what we're using for our implementation. Two unidirectional channels of messages. So this is serializes, that's the first thing, it serializes our chat messages to and from bytes. So what this does is chat connection provides two unidirectional channels of messages. Now the chat connection also does some other things. It also handles keep alives. And it does this by periodically sending keep alives. Periodically sends keep alive messages. And it also ignores incoming ones. And then our chat connection also does something else. So that, this is where it's really, okay, it's doing a lot now. But it also handles that higher level request response. Okay. Michael asks, it's working with .NET Framework and .NET Core, right? No dependencies to anything else. So our implementation does use system.io pipelines, which I believe works just fine on .NET Framework, although I've never actually tried them on that platform. I've always used them on .NET Core. I know they're more efficient on .NET Core, but they should work just fine on .NET Framework. And I think, is that all we've got? Oh, and the system channels, the system threading channels, we've got that too. Let me just double check here. Yeah, those are the only two dependencies we have, system.io pipelines and system threading channels, which should work just fine on both .NET Framework and .NET Core. These are both .NET Core apps, but it should work just fine on .NET Framework. Also in the chat, pipeline socket, there's a magic 4 for the prefix length size. Is there? I did not. Oh, there is. You're right. Look at this right here. So, good catch. Good eye. I'm going to do that. So this is under message serialization. Right. Dot length prefix length is what we want. All right. Good catch. Good catch there. And Lars says, async enumerable may be rewritten. I'm not sure what you mean by that, Lars, by may be rewritten. If you think it may be cleaned up, that's possible. So the other thing that our chat connection does, I mean, you can feel free to post something clarifying in the chat. There's like a 30-second delay. So I'm going to jump back to this real quickly. And the other thing that it does is it handles responses for our requests, right? It also, so I guess just request response matching. Matching? I'll say logic and then say has a collection of outstanding requests and then handles response messages by completing their matching request. All right, we'll say that. So this chat connection is actually doing a fair amount of work here, and I'm really tempted to break it up. And what we would end up then is actually, we would still have that 2 unidirectional channel API, just for a basic, have like one type just doing the serialization, another type then we could add on to just handle keep alives and sending and receiving them, and then another type added on that just handles like the request response, the higher level logic, while also exposing the underlying channel as well. So I think that I haven't actually looked into it, but I think that that's the idea behind David Fowler's work that he pointed out at the beginning of this whole series. I'm going to see if I can find that real quickly. Sorry, I should have had this prepared. I'm searching in my... Here we go, Bedrock. That's what it's called, Bedrock. So if we, I think it's GitHub Bedrock. I know I was looking at it not long ago. Microsoft Bedrock. That's not what it is. I'm going to look for David Fowler's Bedrock. There we go. Bedrock Framework. Okay. So this is something that David Fowler pointed out over Twitter, and I think the idea of this, I just like read some of the docs about it. I haven't dove in and used it at all. But I think the idea is that they have this middleware and then transports. So I think that like the transport would be our, like the socket, the pipeline socket, and then the middleware would be essentially like if we were to split our chat connection up into 3 different types, those would be like middleware for the Bedrock framework. So this is definitely something worth taking a look at. Like I said, I haven't done it. I'm just doing plain old sockets API, Berkeley stuff. But definitely worth taking a look at if you're interested in possibly a much cleaner implementation of this kind of chat connection type here. Okay. So Lars says async enumerable may be rewritten for .NET Framework. There is a boy, I don't remember if it has been a while. But I think that there is a type or a package that supports that. I'm pretty sure there's a way to get async enumerable working on .NET Framework. It's just been a while for me. So Michael says creating the bounded channel can maybe also be set in the constructor. Possibly. The thing is that 4 is kind of arbitrary. This is the 4 he's talking about over here. So these, they just have to be bounded, and they should be small. They should be small. This could be 1, really. I think, yeah, it could be 1. So, because this isn't really our main buffer is in our pipelines, and this is we just need a bounded channel. We're not doing a lot of buffering here. So this could be a constructor parameter, and I mentioned when I added this one, the keep alive time span. If you really wanted to make this like into a true API, this should really be on an options type, right? That has your keep alive time span, and maybe some other things like your incoming and outgoing buffer sizes, things like that. That I'm gonna leave as an exercise for the user. I always hated it when books said that in college because like, really, you're not doing that. Lars says Microsoft BCL async interfaces. Okay, yeah, I think that's the package. Yeah, so there is a way to like get async enumerables working on .NET Framework. Pretty sure. Again, it's been a long time since I've done that. All right, so we are at 25 minutes, and I haven't gotten very far here. We might be extending it one more day. So I've written up the chat API architecture. I want to talk now about things that I didn't cover in this video series deliberately, and things that you might actually really want to do, especially if this is like a publicly accessible API. So first off, I really recommend you don't do that. People who write TCP IP-based servers that are accessible over the public internet have to deal with a whole slew of other things. My experience, and I think the experience of most TCP/IP developers, are on dedicated networks. You're talking to embedded devices or whatever. You know, you have a very controlled environment is the idea. As soon as you're out on the internet, there's a whole slew of things you have to take care of, and really you need a whole team of developers supporting any kind of application like that or framework like that. You know, the people who do ASP.NET, that's not one guy at Microsoft, right? SignalR, not one person. That's not a single person team. You know, that kind of thing. So I want to talk about what's not covered, right? So this is, I'm trying to think of what this title would be. What's missing? So let's see. I'm just gonna say this. Okay, I'll just make a list. So the number one thing is security. I've been completely ignoring security the entire way through this video series. But guess what? You can't ignore security when you're on the public internet. Security is very important. So I'm just going to call out a few things here. Things that you'll want to address if this is, you know, before taking it, before allowing anything else to connect to it, right? Other than some kind of controlled environment. So the very first thing that comes to mind is encryption. Our current protocol is just a plain text protocol. And you're not going to want that, right? You know, just for privacy reasons. The other thing is server and client authentication. Again, this usually ties in with encryption. If you're doing something like TLS. Somebody was working on a TLS over pipelines. You know, we've got the, what's it called? SSL stream, maybe? There's a type in .NET that does essentially TLS over streams, over a streams API. So it consumes an underlying stream and then exposes a stream API to its consumers. And somebody was working on the same kind of thing. It would do TLS, but it would consume a pipeline API and expose a pipeline API to its consumers. But I don't know whatever became of that project. I don't know if it was ever actually completed, but it might be out there if you're interested in that kind of thing. And so that handles encryption, and also, you know, you can do server authentication, and I think you can opt into client authentication as well. So, you know, using some kind of protocol like that usually handles both of these concerns. And then we've got misbehaving clients or servers. This usually requires like a more complex. Okay, so the things you want to deal with here are things like trickle attacks, right? So somebody connects to you and then says, okay, I'm going to give you 64K or whatever. All right, that's a fine buffer size. You're ready for it, and then they send you like 1 byte every, 10 seconds or something like that. So the idea is that they're consuming resources without actually giving you a way to react to that. And I'm gonna put denial of service as a separate one here. But any kind of misbehaving clients or servers. So I'm gonna say this app assumes correct implementations. Or correctly formed packets. How's that? So we'll say this concern is more around whether the packets are correctly formed or not, and I'm going to say denial of service is like a separate concern under security. So this could be really large buffers. So if somebody sends you like this huge length prefix, we have some protection against that, right? I'd put in a maximum message size. Mainly because I wanted to size my pipeline to that so that we would always have enough pipeline buffer space for a single message, which really simplifies the parsing logic. So like really large length prefixes, if we didn't have that guard in, that would be a problem. Or say, I don't know what it's called, but like a drip attack, if that's the right thing. Or like slowly sending data. Or sending data too slowly, I'll put it that way. All right, so that kind of like denial of service attacks, we don't have any protection against that. The other possibility is reflection attacks. And this is something that you do need to be aware of in your protocols. In TCP/IP protocols, it's usually not a huge concern, but in our specific case, we do have that broadcast message where one connected client can cause the server to send a message to all of their clients. So this is the kind of thing like if they're sending large messages all the time, there's no protection against that right now, right? So this is like a broadcast huge message at a high rate, or something like that. So these are the kind of things that you have to keep in mind with security. Where you have to put, not just implement the protocol, but then you have to put these like usage guidelines on the protocol as well. And I'm not doing any of that in this because that gets down into the weeds of, well, how do we want this app specifically to behave? And so that's less useful as an example. The current example code is using the bare minimum chat protocol as an example of how to actually write a TCP application. All right, and what else am I not doing? Right, so the higher level things. So we're talking about, putting on usage restrictions. There's also often when you're writing a TCP/IP application, what you're doing is, some kind of control software or something like that for an embedded device. That's, I would say, pretty easily the majority of TCP/IP applications out there. The ones that we're going to write, right? So the other thing is something that's kind of more common with control software, and that is any kind of like a higher level state, right? Like a state machine. For example, retrying connections if a connection drops. We don't do that at all. Right now we just, the server side says, well, this one went away. And the client side says, oh, I lost this connection. But there's no retrying, right? The client doesn't automatically reconnect or anything like that. Normally, if you're writing software that's talking to an embedded device, you want to just automatically retry to connect. So it'd be like a retry. So when connection is lost, retry connection after some timeout. And just actually, I do want to point this out on my TCP/IP sockets frequently asked questions. I do address this in the error handling. So I talk about here how to respond to errors. Just close the socket. We handle that properly right now. Down here, under retry timers is more what I'm talking about now, where, and usually what you want is when you say connect on the client, what you want to do is keep trying to connect, right? And time out and retry. And so you want like, you need a retry timer, right? So you need to slow down your rate of trying to establish this connection or send this command or whatever. So a retry timer is necessary so that you don't retry too quickly. Like if your network connection was unplugged or something, right? You would just retry immediately all the time, and that would essentially lock up your user interface, which isn't nice. So you want a retry timer for any kind of like socket errors. There are certain cases that I point out in here, that the timed out and connection refused. Those are more common socket errors that you don't actually need the retry timer for. I mean, you could skip it, because in the timed out case, you actually have the network has been trying to send data and it eventually timed out and couldn't send it. So there's already been some time since that initial connection attempt. And then the other one, the connection refused, actually does happen when that packet has gotten to the other computer and then the other computer sends back, no, you cannot connect. So these are a couple of cases where you don't have to have the timer. You can retry immediately because that network round trip takes a non-zero amount of time. But generally speaking, you need a retry timer. So, but anything around that, I'm not including in this. And then the other thing that I wanted to point out here, consider a desired state pattern. And by that I mean, I'm going to type this out instead of just saying it. So the user indicates the desired state, and your application does whatever connection and messages are necessary to, does is a really horrible word there, and your application performs whatever connection and messages are necessary to achieve that state. Okay, so this is just I think it's a pattern that really works well, especially if you're talking to embedded devices, where your user interface is actually well, we could actually use our chat client as an example here. So to kind of show what I'm thinking here. So when we start our chat client up, oh boy, my computer's slow. Right now it's different buttons for everything. We connect, disconnect, send, set our nickname. But really, if I were like designing a proper UI, I would probably have the nickname, be up here, and have that like implicitly immediately sent on the connect. So we would say, connect, and maybe have a server. We would have a server address in here too. That's also completely missing. But we'd have our nickname and our server, and then you click the connect button once. And then what this does is it puts this application, our client application, into this desired state of I want to be connected and I want to have this nickname. So then on that retry timer, or using the retry timer if necessary, we would try to connect, and once we connect, we try to set our nickname. And maybe we get the NAC back, and then we have to kick that back to the user saying that nickname's already taken or whatever. But the idea is we have that desired state. So if we even if we lose a connection, at any point while the user is using this program, we will automatically try to reconnect and then set our nickname right away. So it drives that desired state, and that's just a pattern that I have found really useful, especially if you're talking to embedded devices. That desired state pattern. All right. So I think that's everything I wanted to cover here, and let's talk about some resources. I'm forgetting how to write my markdown. There are some useful resources. There's TCP/IP Illustrated, which is, actually I linked to it from down here, don't I? Yes. So I'm just going to stick that same link over here. This is a book that, and you really only need volume 1. This is a book that really helps. Well, this is the book that I learned TCP/IP from, essentially. It is very thick. I couldn't find it. We still have a bunch of stuff. We moved not long ago, and I still have a bunch of stuff that isn't unpacked yet. So I gotta. But it's like this thick, right? It's this massive tome, but it's a fantastic book. Bring this up here. Yes, this is it right here. Last purchase 2002. All right. I don't think this is quite right. Apparently, Amazon thinks that this book has had more than 20,000 editions, and I don't think that's correct. Actually, I believe that there is a newer edition. Yeah, here we go. Because, yeah, there is a second edition. And one of the things that they actually added in the newer edition, believe it or not, is the state transition diagram. This was originally in volume 2 in the original one. But if you look at, you can, it's on Google these days. It wasn't back when I was writing this, but this right here, this diagram right here, is from that book. And this is, if you are working in TCP/IP and you're not sure what's this time wait, you know, that's the common question. What's this time wait state? But these are actually all the different socket states that a socket connection goes through. And it includes all the things like half closed and all that in here. Even the things I don't recommend you do. But this is the most important diagram for TCP/IP. It's in the inside cover of volume 2, which you don't need. But I think the current edition of volume 1 also has this, and just printed right in the inside cover of the book. It's fantastic. Very, very useful. All right, so I've got that book on there. What else do I need? Oh, I'll stick a link to my blog in here, of course. This will be my TCP/IP .NET frequently asked questions. All right, which I've referenced several times throughout this video series. Lars says, Poly is a good framework for retries. Yes, absolutely. I always use Poly for retries. So when I say a retry timer, yeah. Like I would almost certainly use Poly for this. I use Poly everywhere, for every time I need to do any kind of retries or anything like that. There are some situations, and I'm not sure if a retry timer, yeah, a retry timer should be fine for that. I was thinking of how you structure the code, whether Poly would quite fit in well there or not, but I think it would. Okay, so you know, there's an older, I don't know if that's still around. I should check that out. Pretty sure it's not in here. All right, I mentioned it up here then, don't I? Yes, the WinSock Programmers Frequently Asked Question. That's what it is. All right, so this is a fantastic. It's got a little almost deprecation notice at the top, and it was last updated in 2011. But it has some. Okay, so it has some good resources on here. This is also a great resource for WinSock, or the Windows socket implementation. Actually, this name dates back to when I first got on the internet. Windows did not come with a TCP/IP driver. Like Windows came with network drivers for other protocols, but it actually did not understand how to do TCP/IP. Which is mind-blowing today, right? Because TCP/IP has taken over the world since then. But back in those days, you actually had to install a program called Trumpet WinSock. I believe Trumpet was the company name, and WinSock was their product that essentially added socket APIs, the Berkeley socket APIs, to Windows. And then, I don't know if Windows bought them or what, but eventually they incorporated essentially WinSock into the Windows itself. And then Windows actually shipped with its own TCP/IP stack. But back in the day, it didn't even come with TCP/IP. So I believe that's where the name WinSock actually originally came from, was that original product that you would add on to Windows. Okay, so anyway, but this is a great resource as well. And this is all going to be like unmanaged, right? This is not .NET code. This is all the actual WinSock APIs. But because the socket class is very, very close to that Berkeley socket API, you can kind of look at this and then take that lesson back to your .NET code pretty easily. And I've done that many times myself. I'm just going to make a note that this is for unmanaged. All right. Illustrated. This is an R. Thank you. Freddie says, I remember we had to install IPv4 in Windows 95. Yes, yes. I think I was, Windows 95, I think, had the actual IP stack at least. Like you might have had to, it might have been an optional install, but it actually was part of Windows. I'm thinking Windows 3.1 was back when you had to install 3.1 sock, but I can't really remember. That was a long time ago. Okay, so I've got some resources on here, and I want to take a look at some tools, and I'm thinking I'm just going to run through this. I'm going to run through some of the tools really quickly. Let's see how far we get. We got 15 minutes, but I also want to add these over here. So the first one to look at is Process Monitor. This used to be a separate app for the network calls, and this is for this is essentially like, so I'm going to go through the tools in order of like closest to the application down to closest to the hardware. So this one is closest to the application, and this actually just shows what WinSock APIs our applications are actually calling. I'm pretty sure Process Monitor does that. It's been a long time since I've used it for that. So this is it's essentially to trace socket APIs called by an application. Fine. We'll just say that. And Process Monitor is at, I don't know, it's on it's officially supported by Microsoft now. It wasn't originally. This was originally developed by Wintellect and by Mark Rusinovich. Oh, it says Mark Rusinovich right there. It was originally developed by Mark Rusinovich back before he worked at Microsoft, and now he's heading up their whole Azure division or whatever. But like back when he worked on when he was working for a different company called Wintellect, he actually wrote several tools. And then when he came on board to Microsoft, I assume part of that agreement was they also got like ownership of these tools, and the TechNet team or whatever it was. I don't know if TechNet is still a thing, but at least at the time, the TechNet team like took over responsibility for these tools in Microsoft. So these are official Microsoft tools now, but they're fantastic tools. Wow. So Process Monitor. Let me just grab that link there. These are tools that really let you dive into the Windows kernel and see exactly what's happening. So if I run this, and let me kick off my chat server as well. Actually, I'm going to run this first. A lot of the tools that I'm going to show here are most useful if you run them before you run the application that you're testing. So I'm going to kick this off, and it starts logging everything. This is like every interesting Windows API call. We've already got 100,000 events. All right, so I'm just going to turn off my capture for a minute, delete everything we've already captured, and then here's our buttons over here that determine what we're going to capture. And man, my computer is really slow. I don't know how far I'm going to get through this. I might just have to make the tools part tomorrow. We will go one more day. I'm going to go over all the tools in detail. I think that sounds like a good plan. I'm not sure what's up with my computer, but this is not going to work. Yeah. So tomorrow I'll have rebooted, and we'll get a better system working here. So for now, I will be back on this tomorrow. Let me check in everything here. What did I do over here? Oh yeah, that magic value. Let's say, so this is day 12 also, and then updating some README. All right, so if anybody has any questions or anything, send them to me over Twitter or ask in the chat for tomorrow. Tomorrow morning is going to be definitely the last episode, almost definitely. And today will be the penultimate one. And I'm going to call that for today. And tomorrow we will wrap up. I'm going to take a look at several different tools, including one that is really, really useful, Wireshark, that I haven't used so far. But I'm definitely going to dive into Wireshark and show how to extend Wireshark even. And yeah, so we'll see you tomorrow for the last episode of TCP/IP application design. Thank you all for coming. This has been part 12, and tomorrow we'll wrap it up. See you then.